Welcome back, chemistry fans. What we're going to do today is the electron dot little activity. So you're going to be needing some of these googly eyes that we use for the nuclear, and we're going to practice putting the valence electrons in the correct order around specific elements. So join me as I switch my cameras here. Cancel that. Hold on. Sorry. Okay. So what we're going to do is we are going to take these googly eyes, and they're going to represent electrons this time. And what we need to do is place these electrons around the elements in the correct positions. So we need to be able to count valence electrons. Hydrogen has one valence electron, so it will get one dot around its 12 o'clock position. Calcium is in the second column. It has two. Both of those electrons are going to go in the 12 o'clock position to represent the two s electrons that are found in this atom. Aluminum has three, so we'll place two again at the top, and then we'll place the third one either on the left, the right, or at the bottom. It does not matter where you place them. These are all equivalent positions because these are all p sublevel electrons. Then comes 4 for carbon. So carbon has 1, 2, and now you would think that you would place both of these together, but you will not. You must separate them according to Hund's rule. So 2 at the top and 1 around each one of the sides. We'll continue now with nitrogen. Nitrogen has 5 valence electrons. So it's going to have 1, 2, 3, 4, and 5. So notice again, it's spreading them out because it has 1 valence electron in each of the corners of each one of the orbitals, representing the p sublevels getting filled with 1 electron each. We have then sulfur, and it has 6. So I have 1, 2, 3, 4, 5, 6 for sulfur. And then we're going to do chlorine. Well, I'm seeing what the pattern is. I bet you guys could probably play this out without my help even at this point. So 1, 2, 3, 4, 5, 6, and then the 7th one is going to go down at the bottom. It doesn't matter if you want to put it over here because you think it makes it look more symmetrical. They're all equivalent positions. It doesn't matter. All right, and then the last one is neon, and it's going to have 8. So I'm going to have 1, 2, 3, 4, 5, 6, 7, and 8. So it will have its entire valence shell filled. It has a stable octet. It is happy. Okay, so this is the first task. Take a picture of your work, just as you see it here. Of your work, not of my work. I should rephrase that. Make sure it is your work, so you are showing that you are participating. All right, next, you are going to then draw the following molecules. You're going to draw H2O and CO2 on here, so enough space that we can move the electrons around and make sure that everyone gets a stable octet. So I'm going to count how many valence electrons the carbon has. We know it has 4. So we'll put 1, 2, 3, 4. Now the hydrogens, I'm going to use smaller electrons so that we can distinguish where the electrons are coming from. Now the goal is that we must get a stable octet for the oxygen and a stable duet for the hydrogen. So it's going to be easy for us to get the hydrogens here because they each need 2. So if I were to look at this model, what I would see is that I have achieved a stable octet around, stable duet around the hydrogen. So I'm going to circle those to represent the fact that it is satisfied. It has 2 electrons around it. And then I'm going to have to, and it's 4 electrons. Jeez, I'm so dumb. So it's 4 electrons around, the oxygen has 6 valence electrons. So I shorted it 2 electrons. So what I need to now show and represent is the fact that the oxygen got itself a stable octet. So again, The oxygen has 6 valence electrons. I mistakenly showed that. The hydrogens each have 1 valence electron. So if I then move the electrons around, I can represent that this one has a stable octet. Okay, now I'm going to fix this with the carbon. The carbon, it only has 4 valence electrons. This is what I should have had on the first example, but I did that incorrectly. The carbon has 4 valence electrons, so I'm going to go ahead and put these around, 2 at the top, 1 at the side, and 1 at the bottom. And you're saying, but these are the positions they're supposed to be in. How can they just move? Because they are going to share nicely so that everyone gets a stable octet. They don't care where they come from. They just want to make sure that everyone gets happy and satisfied. It's a nice world to live in, an atom that is sharing. So my oxygen is going to each have 6, but we got to make sure that we put the correct number of electrons, A, and that you have represented a stable octet for everyone. Whoops, just moved everything off of here. That's okay. 1, 2, 3, 4, 5, 6. Okay, so this one is okay. Now I'm going to put this oxygen over here with the 6 as well. 1, 2, 3, 4, 5, 6. Okay, now this one takes a little bit more effort. Now you can see already that there is some sharing going on here with these oxygens here, and that I'm not adding any more electrons mysteriously, not like last time. I am actually just showing that there is a stable octet needed for each one of them. So how are we going to move electrons? It doesn't matter where they come from. I can put this one over here, and now I have a stable octet around the oxygen. But this oxygen over here does not yet have a stable octet. So I can move this one over here. I can move this one over here. Now this oxygen has a stable octet. But what do you notice about this carbon? It does not have a stable octet. So I'm going to introduce a method next class where we solve this problem. You don't have to do a guessing game. So what is actually going to happen is we're going to change the possibilities. We're going to create a double bond. So we are going to create a scenario where now, because I am sharing more than 2 in between, I achieve 8 around the oxygen. I achieve 8 around the carbon, and I also have achieved 8 around this oxygen over here. So these are called Lewis structures whenever we start dealing with atoms, with molecules, but whenever they're just atoms, it's called the electron dot. So this is everything that I was hoping you would practice with me. So thank you very much for your time. I'm going to leave you with one that I want you to practice on your own. So you're going to come up with one on your own. Are you ready for it? You are going to do the following. Let's see. Let's do SO3. Let's see if you can figure out how to get everyone with a stable octet around this, okay? And it may not work out where it's symmetrical. That's your task. Try and practice it. Thank you very much. I will talk with you again soon. Bye-bye.